Proxima Centauri, the closest stellar neighbor to our solar system, has long captivated astronomers. This diminutive red dwarf, identified in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also encompasses Alpha Centauri A and B, despite its proximity, just 4.24 light-years away. It remains invisible to the unaided eye due to its relatively low luminosity. However, Proxima Centauri holds immense scientific significance, particularly as the host star of Proxima B, an extrasolar planet in the star's habitable zone. Red dwarfs such as Proxima Centauri are smaller, cooler, and have significantly longer lifespans than stars like our Sun. Their low luminosity makes them challenging to observe, but it also means their habitable zones are significantly closer to the star. For Proxima Centauri, this translates to an orbital distance of just 0.04856 astronomical units, a mere fraction of the distance between Earth and the Sun. Proxima B is subject to intense stellar activity, including frequent solar flares and radiation, creating an environment starkly different from Earth's. The discovery of Proxima B was a monumental achievement in exoplanet research. Using the radial velocity method, astronomers detected subtle wobbles in Proxima Centauri's position as a result of the gravitational pull of an orbiting planet. These wobbles allowed scientists to estimate the planet's mass and orbital period. The European Southern Observatory officially confirmed the existence of Proxima B, marking a breakthrough in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima B, they have significant limitations. Atmospheric distortion and light interference hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of the information we have, including its mass, distance from the star, and orbital characteristics, relies on indirect measurements to uncover deeper truths about Proxima B's environment and its potential for life. More advanced observational tools like the James Webb Space Telescope, JWST, are indispensable. Proxima Centauri's role as a gateway to comprehending exoplanet systems cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B, in particular, embodies an enticing possibility: a rocky, Earth-sized planet with the potential to harbor water and perhaps even life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists to solve. The James Webb Space Telescope JWST is more than just a new tool in the arsenal of astronomy. It is a revolutionary instrument designed as the successor to the Hubble Space Telescope. It was intended to address the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided valuable information about the cosmos, its capabilities are constrained by its focus on visible and ultraviolet light. JWST, in contrast, is built to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and discover phenomena invisible to Hubble. One of the key design features of JWST is its primary mirror. With a staggering diameter of 6.5 meters, more than double the size of Hubble's mirror. The wider mirror enables JWST to collect far more light, making it capable of observing extremely faint and distant objects, coated with a thin layer of gold to enhance its infrared reflectivity. The mirror is comprised of 18 hexagonal segments that collaborate to produce a highly sensitive observational platform. Another groundbreaking innovation is JWST's 5-layer sunshield, which keeps the telescope's instruments at a constant temperature of about. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. It's unlike Hubble, which orbits Earth. JWST operates from the second Lagrange point L2, a stable position approximately 1.5 million kilometers from our world. This location minimizes interference from Earth's heat and light, enabling JWST to conduct continuous observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its focus on infrared light is particularly significant, as it allows astronomers to study red-shifted objects, whose light has been stretched to longer wavelengths as the universe expands. The capabilities of JWST go beyond mere observation. It is designed to answer some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that might support life on other planets. With its state-of-the-art instruments, including the near-infrared camera IRCam, the mid-infrared instrument MIRI, and the near-infrared spectrograph IRSPAC JWST, is not just a telescope. It is a time machine, a laboratory, and a beacon of ingenuity. Proxima has captivated scientists and the public alike as a potential second Earth. Located within the habitable zone of its star, the planet has the right conditions to potentially support liquid water, a key ingredient for life as we know it. With a mass roughly 1.17 times that of Earth, Proxima B is most likely a rocky planet, similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for investigating the possibility of life. Beyond our solar system, however, Proxima B is far from a perfect twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight while the other remains in total darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, may offer a narrow twilight zone with conditions suitable for life. The difficulties posed by Proxima B's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can emit bursts of X-rays and ultraviolet light. These flares could strip away the planet's atmosphere, over time, exposing its surface to the harshness of space. If Proxima B retains an atmosphere, it likely requires a strong magnetic field to shield it from radiation. Without such protection, the surface environment is hostile to life as we know it. Despite these challenges, scientists are optimistic about the potential for life on Proxima B. The planet's position within the habitable zone suggests liquid water could exist on its surface or in subsurface reservoirs. Life might adapt to these difficult circumstances. Much like extremophiles on Earth's organisms that thrive in extreme environments, such as hydrothermal vents in the deep sea or higher radiation areas, these adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima B is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima B represents a tantalizing possibility, a rocky, Earth-like world that might harbor the conditions required for life. As our technology advances, so too does our ability to explore this intriguing planet and uncover its secrets. While Proxima B offers enticing possibilities, its environment is profoundly shaped by the nature of its parent star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf star, smaller, cooler, and far less luminous. Due to its reduced size and temperature, the habitable zone lies much closer, drawing Proxima B into an orbit roughly 0.05 astronomical units away, approximately 20 times nearer than Earth's orbit around the Sun. This closeness introduces a unique array of challenges for both the planet and any potential life it may sustain. Primary concern is Proxima Centauri's heightened stellar activity, particularly its strong and frequent eruptions from the Sun. These flares are abrupt, potent discharges of energy that unleash substantial amounts of X-rays and ultraviolet radiation. Compared to stars like our Sun, red dwarfs generate these flares more often and with greater intensity. For Proxima B, this results in continuous exposure to high-energy radiation, which could gradually erode the planet's atmosphere. Void of a protective magnetic field, any existing atmosphere would be vulnerable to being stripped away, leaving the surface bare and exposed to dangerous radiation. Even if some atmospheric layers endure, Proxima Centauri's intense radiation presents serious hurdles for the emergence or persistence of life. High levels of ultraviolet radiation can cause severe molecular bond damage, obstructing the creation of complex organic structures. This would severely hinder the likelihood of life developing or thriving on the surface. On Earth, resilient microbes, such as Deinococcus radiodurans, have evolved to withstand radiation by repairing DNA damage, implying that life on Proxima B, if it exists, might have developed similar or even more advanced survival strategies. However, the degree of radiation resistance needed would be extraordinary, possibly requiring entirely unfamiliar biochemistry. It's interesting how the tidally locked nature of Proxima B might offer certain advantages. Confronts the assault of stellar radiation, the perpetual night side might serve as a shelter. Environments that are underground or in deep planetary caverns could protect potential life forms from radiation. Likewise, if Proxima B harbors subterranean oceans, these could act as sanctuaries, offering stable, shielded environments comparable to the hydrothermal ecosystems found on Earth's ocean floor. Despite the significant challenges, researchers remain hopeful that Proxima B's harsh landscape presents a valuable opportunity to examine how life could survive in extreme environments. Exploring the potential resilience and adaptability of organisms in such conditions enables scientists to expand their understanding of habitability criteria across different worlds. Proxima B is not merely a candidate for extraterrestrial life. It serves as a living laboratory for examining the thresholds of biological endurance. Its relative proximity to Earth and its location in its star's habitable zone make it a prime subject for ongoing investigation. With the advent of next-generation space observatories and tools, astronomers are better equipped than ever to study this intriguing planet for signs of life-supporting environments. Although significant challenges lie ahead, Proxima B offers a compelling preview of the kinds of life-supporting conditions that might be found in other parts of the galaxy. It reminds us that the pursuit of cosmic knowledge and the search for life on other planets is still in its infancy. The exploration of life outside Earth is far from complete. The detailed examination of planets like Proxima B plays a vital part in expanding our comprehension of what conditions are essential for life. One of the core reasons Proxima B is so fascinating is its rocky shape and Earth-like size and composition, positioning it as an ideal reference point for evaluating the potential habitability of planets orbiting distant stars. Scientists are especially intent on identifying exoplanets that resemble Earth, as these are the most likely to provide conditions suitable for biological activity. To find out more about whether life could exist on Proxima B, astronomers are making use of cutting-edge techniques to study the planet's atmospheric composition and environmental traits. One particularly promising approach is transmission spectroscopy. This method involves observing the filtration of starlight through an exoplanet's atmosphere during transit events. The way light is absorbed reveals the chemical makeup of the atmosphere. By inspecting absorption lines in the light spectrum, scientists can identify specific gases, such as oxygen, methane, and carbon dioxide, which on Earth are closely linked with biological processes. Recognizing such gases around Proxima B would serve as compelling evidence for the presence of life-supporting mechanisms in parallel. Researchers are looking into the possibility that microbial life might exist beneath the planet's surface. The idea of subsurface life has recently gained momentum, particularly with the discovery of extremophiles on Earth that survive in what were once deemed inhospitable environments, like deep-sea vents or highly acidic lakes. If Proxima B harbors underground water sources or aquifers, these could serve as safe havens, shielding life from the planet's severe radiation. Such environments would greatly enhance the likelihood of discovering microbial life adapted to extreme conditions, much like those found in Earth's deep oceans, beyond the hunt for life. The study of Proxima B provides a broader opportunity to comprehend the driving mechanisms of planetary systems. Its location within a red dwarf's habitable zone provides a unique platform to explore how star-planet interactions determine atmospheres, climates, and magnetic environments, all crucial components in determining whether a world can sustain life. For instance, Proxima Centauri's relentless solar flares could play a significant role in shaping weather dynamics and long-term atmospheric stability on Proxima B. Understanding these influences helps astronomers evaluate the broader conditions necessary for habitability across different types of star systems. Though we are still early in studying Proxima B, advanced tools like the James Webb Space Telescope allow scientists to investigate its mysteries more thoroughly. JWST's ability to observe in the infrared spectrum will facilitate more refined studies of the planet's surface and atmospheric features, gaining access to data that may support or rule out the possibility of it supporting life. Of exoplanets grows, Proxima B will remain a central figure in the search for a response to one of humanity's most fundamental questions. Is there life beyond our planet? Ultimately, the research into Proxima B is not solely about discovering extraterrestrial organisms. It is also a journey toward comprehending the universal concepts that make a planet hospitable. Gaining insights into the prerequisites for life can assist us in enhancing our search for living worlds across the cosmos. The study of Proxima B represents just one chapter in an expansive narrative, our ongoing endeavor to map and understand the vast universe beyond our own. Additionally, it offers crucial clues about planetary formation and stellar evolution, particularly in systems orbiting red dwarfs. By analyzing the relationship between Proxima B and its host star, scientists can better comprehend the dynamics of close-orbit planets and the forces that shape their development.